All right, we are on to 11.3. So for this lesson, I've allotted you 2 days. The first day, the idea is to get through the notes. And then the second day would be to work on the page of practice problems and then the homework. Okay, so you don't have to do the homework today unless, just totally get it. Get through stuff really quickly. So for this lesson, I'm going to have to switch back and forth a little bit between my phone. I'm going to use the board actually once or twice. So I don't have to totally keep switching back and forth because that gets really annoying and frustrating. So let's start with, that's not what I wanted to do at all. There we go. Okay, so we'll start with the PowerPoint. I'm filling in your notes a little bit. So we're going to start by talking about gas volume, and we're going to talk about how you can see on your notes you have a couple of laws. So you have Gay-Lussac's law of combining volumes and how that works, and then we're going to talk about Avogadro's law, which is how we can use a balanced equation and use, instead of a mole ratio, we're going to relate the volumes. Okay. So we're going to start with Gay-Lussac's law. And what he's saying is if you have an equation, if you have a chemical equation where all of the participating reactants and all the products are in the gas state, then you can interpret the equation in terms of the volume. Okay. So for instance, so the reaction that he observed was reacting hydrogen gas and oxygen gas, and it produces water. So if you balance that equation, it takes two volumes of water, two volumes of hydrogen, a volume of water, and you get 2 volumes of water vapor. Okay. So you do 2 liters of hydrogen, you would react that with 1 liter of oxygen, and you would produce 2 liters of water vapor. Okay, as long as you keep the pressure and the temperature the same, this law holds true. Okay. So yes, okay. Avogadro's law is the second thing we need to discuss before we can move on. Avogadro's law states that if you have equal volumes of a gas, or of 2 different gases, you have the same volume of those 2 gases, and you have them at the same temperature and the same pressure, doesn't matter what that temperature and pressure is, as long as it's the same, they will contain the same number of molecules. So this is what we call standard molar volume. So this is the same guy that came up with the number of molecules in a mole of any substance. Now we have a mole of gas, the volume of 1 mole of gas at STP. So if you have 1 mole of any gas and you put it at standard temperature and pressure, it's going to be 22.4 liters. Okay, we'll occupy that volume every time. Okay, so that's Avogadro's law, and we can use that as a conversion factor. So 1 mole of any gas is 22.4 liters, or 22.4 liters is 1 mole of gas. Okay, so we can use it either direction, and we are going to practice that. Here in just a second, I'll give you a second to write those 2 down. But we are going to practice this. Okay, so this one I have animated. And it asks, what volume would 0.0685 moles of gas occupy at STP? Okay, so we start with what we're given, the 0.0685 moles. It's at STP, so the volume is that 1 mole is equal to 22.4 liters. We would put the mole on the bottom so that our moles would cancel, okay? And so when you do the math, you end up with 1.53 liters. Okay, so any gas, if you have 0.0685 moles of that gas, it's going to take up a volume of 1.5 liters at standard temperature and pressure. Do you remember standard temperature and pressure? What are their values? Say it out loud. You should have said, hopefully, 0 degrees Celsius and 1 atmosphere. All right, so this is going the opposite direction. We are figuring out how many moles do we have in this volume. So if I have 2.21 liters at STP, how many moles is that? So this time I'm going to put the 22.4 on the bottom so that my liters cancel. So I would divide 2.21 by 22.4 and find 0.0987. Okay. All right, so this is the one where I'm going to switch back to the camera. I'm going to do the third one. You should pause the video and try the third one on your own. I'm going to put it on the board and mute myself. Okay, so if you have an experiment that requires 0.0580 moles of nitrogen monoxide, what volume would you need at STP? Okay, so to do this, I start with my 0.05. Oh, it's backwards for you. That's delightful. Okay, so never mind. I'm going to tell you the answer, and don't worry about that. If you are not sure how I get the answer, maybe one of you can figure it out. If not, message me and I will try to get back to you. So 0.0580 moles of a gas at STP, the volume should be 1.3 liters, roughly. You may have to round to get that answer. All right. So let's share again. Okay, so that was that one. Okay. Okay, now we're bringing back our lovely word, stoichiometry. Remember, that's just conversions, using the balanced equation like a recipe to convert between different factors or to convert to mass. So with gas stoichiometry, what we're saying is that our coefficients that we have in a balanced equation can tell us the number of moles. We've already done that. That was chapter 9, and molecules. Did that in chapter 9 too. Now we're adding in volume. It can tell us the relative number of volumes. Okay, and so then we can use these different conversion factors to convert between any of them. We can convert moles to volume, which we just did. Okay. Or we could convert to mass eventually, okay, by using molar mass. So if I can use the molar volume to figure out how many moles I would have, then I can go from moles to mass. All right, so here we have, here we have an example using propane. And it gives us the equation for the complete combustion of propane. And it asks us, first of all, it just asks us to figure out how much or what volume of oxygen would be required. So if I have 0.35 liters of propane, what volume, how many liters of oxygen do I need? So this, I'm just going to do a volume ratio. Okay. So I have, if I use my coefficients here, so I have a coefficient of 1 for the propane and a coefficient of 5 for the oxygen. So I can use, I would set it up this way where my volume of propane is on the bottom, my volume of oxygen is on the top, right? Because I want to divide away. I want the propane to go away and be left with oxygen. Okay, and so I use those coefficients as a ratio. Okay, so in this case, I'm going to multiply 5 times 0.35. So I would need 1.75 liters of oxygen to react completely with that amount of propane. Okay. All right, so now I'm going to switch to my phone. That's not what I wanted to do at all. Let's see if it'll work this time. Hopefully. Hey, there we go. All right. We're actually not on this page anymore. All right, so we are here at B. So now we're going to figure out the volume of carbon dioxide gas that's going to be produced. So I am again starting with that 0.35 liters of propane. So my 0.350 liters of the propane, C3H8. This time I'm figuring out the volume of carbon dioxide, so it's the same process. So I look at my equation up here, 1 liter of C3H8 is going to produce 3 liters of CO2. So I would just multiply the 0.35 by 3 this time. And I get 1.05 liters of carbon dioxide. Okay. So you should pause at this point and attempt the next one down here. It's weird just because it uses xenon. Okay. So you first need to write the balanced equation. So you might want to start by writing out an equation and then come back and check and see if you wrote the correct equation before you move on. And then it wants to, then it gives you, so write the balanced equation, and then it gives you a volume of the product, the xenon hexafluoride. And then it wants to know how much of the xenon and fluorine should be reacted. Okay, so this one is saying that we have, now is when you pause and attempt to write your own equation. And I bid you good luck because you weren't real good at that. All right, so xenon is reacting with fluorine. So my, excuse me, my equation, I have xenon as a gas plus fluorine. And remember, fluorine was diatomic, okay? So it's F2. And that is going to produce xenon hexafluoride, CeF6, also as a gas. Okay, so my balanced equation, I just need to put a 3 right in there. All right, so if you've got the balanced equation, try and figure out, based on 3.14 liters of your product, how much xenon would you need and how much fluorine would you need. So 3.14 liters of the XeF6. I'll go to xenon first. That's the first one it asks for. So we have 1 liter of XeF6 and 1 liter of Xe. So you would need 3.14 liters of xenon. Okay, but my equation would look a little differently for the fluorine because I have 1 liter of xenon hexafluoride, but 3 liters of fluorine. So multiplying that by 3 gives me 9.42 liters. And I'm not on the screen once again. Fluorine. Okay. So it asks you to find both, so you should have found both volumes. For this one, you need to make sure you're telling me in some form or fashion which one you're finding, which reactant you're finding. Okay, so either, and it would be best to do it in both places, either making sure you write out which substance you have in each of your boxes here. That would be good to do anyways. Don't be lazy. But also in your final answer, making sure you indicate which product or reactant you're finding. All right. So now we're going to move on to the ideal gas law. So I'm going to switch back over to here. Keep going. All right. So you don't necessarily need to write all of this down. I know some of you are going to try anyways. So the ideal gas law is going to relate pressure, volume, and temperature. Ooh, that was a terrible line. Okay, which we related with the combined gas law, but we're also going to throw in here the number of moles. Okay, so the definition of the ideal gas law is this relationship, this mathematical relationship between pressure, volume, temperature, and the number of moles. Okay, what you need to make sure that you know is this part right in here, this second point. Okay, so it gives you the equation, PV is equal to nRT. So P is still pressure, V is still volume, T is still temperature in kelvins. N and R are new, and so it tells you here what N and R are representing. N is the number of moles. You're either going to solve for that, or you're going to be given that in moles, okay? R, however, is a constant. Okay, it's actually called the ideal gas constant. It can be measured in several different ways based on your units, and there's a chart in your book that shows you all of those. The one we are going to use is that R is equal to 0.0821. In order to use this value for R, you have to have your volume in liters. You have to be using moles. So if they give you a mass, you have to convert that to moles. You have to be in Kelvin, and you have to be in atmospheres for the pressure. Okay, so if you, as you're going along, doing the practice problems, make sure that everything is in these units. Okay, liters, moles, Kelvin, and atmosphere. Okay, so there are different values for R if you change any of those things. So temperature is always in kelvins, and N is always in moles. But if you use pressure in kPa, you would use a different value for this. Okay. But we are going to, and the stuff with your textbook is applying it at 0.0821. We're going to try to use liters, atmospheres, moles, and Kelvin. Okay. So this middle point is the one that you really need to make sure that you have written down. If you want to write this in, you may have to come back to the notes another time and finish writing in those units. Oh, erase that. Okay. I knew there was a. Okay. So now we have a practice problem. I think I have this one animated. So it gives us some information. It wants us to calculate the pressure. Okay, so what is the pressure in atmospheres exerted by a half mole sample of nitrogen gas in a 10-liter container at 298 Kelvin? So it gives us moles, it gives us liters, and gives us Kelvin. Okay, so if we go back, maybe. So we have moles, liters, and Kelvin, and we're finding atmospheres. So good, we can use our value that we need. We can use R as 0.0821. Okay, so my equation is that, so we're going to find pressure. So my equation is PV is equal to nRT. So when I rearrange this, right, I can just divide V to the other side to solve for P. So I'm going to do nRT divided by volume. Plug in my numbers. So for this one, you could enter this in one step. A half times 0.0821 times 298, divide by 10. You should get 1.22 atmospheres. Okay. So it's as easy as that. So just double check as you're doing the practice problems to be sure that you have your units in, or have your values in the correct units. Okay. We have one more problem, and I am gonna again switch to my phone. So sorry that it takes so long to switch back and forth. Okay. We'll do this last problem, and then that's the end of this lesson. If you guys still have plenty of time in class, I would recommend that you go ahead and start on the practice problems. And then tomorrow you can finish those up and then start on the homework. And I'll look at your homework here in just a second. We'll look at the practice problems and the homework. So I'm going to recommend again that you pause the video, attempt this on your own, and then come back to it and check your work. Okay, so we have a volume of 2.07 liters. That's the right units. We know that N is equal to 2.88 moles. Well, that's the right units. And a temperature of 22 degrees Celsius, which is not the right units. However, I can convert it. 22 plus 273 is 295 kelvins. Okay, so my R value is going to be 0.0821. And again, I'm going to find the pressure. Okay, so we just rearranged it. So pressure is equal to nRT divided by V. So it's equal to 2.88 moles times 0.0821 times 295 divided by the volume 2.07. So 2.88 times 0.0821 times 295 divided by 2.07, and that gives me 33.7 atmospheres. Don't forget your units. Remember, numbers without units are wrong. They're useless. Okay. Nice. I don't actually count the whole thing wrong, but I should. So make sure you include your units of atmospheres here. All right. So let's go look and see what we have. Switch back over. Yeah, that is wrong. Okay. And this, all right. So this is your practice. So you're going to look at the first little bit is just converting moles to volume or volume to moles. Make sure that you can do that. Bring in density. Remember, density is mass divided by volume. So if you have the density, you've done this before. If you have the density, you should be able to find the molar mass because you know molar volume. Okay, so try number 5. And I will leave an answer key, of course. And then the last problems are all ideal gas volume, ideal gas law. So the first one, again, you're solving for pressure, and then you get one where we're finally solving for something other than pressure. You have to solve for the volume. And I believe that there's one solving for mass, so you're going to have to find the moles and then convert that, use the molar mass. Tells you what substance you have. Use the molar mass to find the mass of the gas, right? Because remember, moles, it's a useful value, but to actually figure out, well, how much do I use, you have to measure the mass of it. Okay. And then we're gonna find temperature, and then the last one you find volume again. Okay, so tomorrow, if you don't get it all finished today, you're gonna do the practice problems and then start on the homework. Go ahead. And so the homework has you doing several things. So the first 2 are multiple choice, and then number 3 has 2 true, false. So pay attention to the fact that that's multiple choice and then true, false. 4 is not multiple choice. 4 is a series of questions that are relating to this table. Okay, and then on the back, you're doing more of the same kind of stuff that we've been doing with the practice problems and with the notes. Okay, so again, send me questions. I will try to get to them as soon as I can. Check out the other videos on Google Classroom if you're confused. That might be more helpful than waiting for me to get to your question and get you an answer. Okay.